On December 24th, 2024, a spacecraft the size of a small car dove closer to the surface of the Sun than any human-made object in history, passing within 3.8 million miles of that blazing surface, close enough that if you shrank the distance between the Earth and the Sun down to the length of a football field, this spacecraft would be standing about 4 yards from the goal line. It survived temperatures exceeding 1,800 degrees Fahrenheit, shielded by a heat shield just 4.5 inches thick, and for the first time in a sustained, meaningful way, it let humanity actually see and directly measure the inner corona, the Sun's superheated outer atmosphere, from the inside rather than from millions of miles away. What that spacecraft found there wasn't simply confirmation of what physicists already suspected. It was the direct physical resolution of a genuine 70-year-old scientific mystery. And the answer turned out to be something nobody had been able to prove existed until this exact mission finally got close enough to check. This is the real story of what NASA's Parker Solar Probe actually found inside the Sun's inner corona, why the discovery solves one of the most persistent puzzles in all of solar physics, and why the details of that answer genuinely surprised even the scientists who had spent years suspecting it might be true. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why actually reaching the Sun's inner corona took nearly 7 decades of theoretical work and required building one of the most technically extreme spacecraft ever launched, you first need to understand the specific puzzle scientists were actually trying to solve. It's called the coronal heating problem, and it's been sitting unresolved at the center of solar physics since researchers first began seriously studying the Sun's outer atmosphere in the 1940s and 1950s. The problem itself is almost embarrassingly simple to state, and that simplicity is exactly what makes it so genuinely puzzling. The Sun's visible surface, the photosphere, sits at a temperature of roughly 5,500 degrees Celsius. But the corona, the Sun's extended outer atmosphere, the layer of plasma sitting above that surface, reaches temperatures between 1 and 3 million degrees Celsius, hundreds of times hotter than the surface directly beneath it. Under almost any other circumstance in physics, moving away from a heat source causes things to get cooler, not dramatically hotter. Standing farther from a campfire doesn't make you warmer. Yet somehow, the Sun's atmosphere gets ferociously hotter as you move outward from its surface. And for the better part of a century, nobody could fully explain the specific physical mechanism responsible for that heating. Researchers had developed real, mathematically serious theories over the decades attempting to explain this paradox. Most centered on the idea of turbulent dissipation, the general principle that mechanical energy, in this case the churning, chaotic motion of plasma and magnetic fields near the Sun, could eventually convert into heat, similar in basic concept to how vigorously stirring a pot of water generates a small amount of warmth through friction and turbulence. The trouble was that near the Sun, in the extraordinarily hot, sparse conditions of the corona, plasma behaves as what physicists call a collisionless medium, meaning individual particles are spaced so far apart and moving so quickly that they essentially never directly collide with each other the way molecules do in the air you're breathing right now. Without those direct particle collisions, the conventional physical mechanisms responsible for converting motion into heat in more familiar, denser environments simply don't apply in any straightforward way. Exactly how energy actually gets converted into heat under these specific exotic conditions remained for decades a genuinely open theoretical question, one that couldn't be fully resolved through mathematics and modeling alone. It needed a direct physical measurement taken from inside the environment itself. That's precisely the challenge NASA's Parker Solar Probe was built to solve. Launched on August 12, 2018, and named after Eugene Parker, the physicist who first theorized the existence of the solar wind back in the 1950s, making it the first NASA spacecraft ever named after a living scientist, Parker Solar Probe was designed from the outset to do something no previous spacecraft had attempted: fly directly into the Sun's corona and take direct physical measurements from inside that superheated environment, rather than observing it indirectly from a safe distance using telescopes. Getting there required a genuinely audacious piece of engineering. The spacecraft carries a heat shield called the thermal protection system, just 4.5 inches thick, built from a reinforced carbon-carbon composite specifically engineered to withstand direct solar radiation intense enough to heat its sun-facing side to nearly 2,500 degrees Fahrenheit, while keeping the spacecraft's actual instruments tucked safely in the shield's shadow at a comparatively comfortable room temperature just a few feet away. To actually reach the Sun, the spacecraft couldn't simply fly there directly either. It required 7 separate gravity-assist flybys of Venus, spaced out over years, each one using the planet's gravity to gradually tighten and shrink the spacecraft's orbit, slowly bringing it closer and closer to the Sun with each pass, building toward its eventual closest approaches. On April 28, 2021, during its 8th orbit, Parker Solar Probe achieved something NASA formally described as unprecedented. It became the first spacecraft in history to fly directly through the sun's corona, spending roughly 5 hours inside that superheated outer atmosphere before exiting back into the surrounding solar wind. That initial pass represented a genuine historic first, the moment a human-made object had, in the most literal sense, physically touched the sun. But it was only the beginning of a longer campaign. Over the following years, the spacecraft continued its carefully choreographed series of increasingly close solar passes, culminating in a sequence of 3 record-setting close approaches beginning on December 24, 2024, when Parker Solar Probe reached its closest distance yet, just 3.8 million miles from the sun's surface. Traveling at roughly 430,000 miles per hour, the fastest speed ever achieved by any human-made object. Close enough and fast enough that mission controllers on Earth had no way to communicate with the spacecraft in real time during the encounter itself, leaving its onboard systems to operate entirely autonomously through the most dangerous phase of the entire mission. It was data gathered during these increasingly close encounters with the corona that finally allowed researchers to directly confirm what had, until then, remained only a compelling but unproven theoretical prediction. In research published in the peer-reviewed journal Physical Review X in 2025, a team led by Jack McIntyre, a PhD student at Queen Mary University of London, working alongside his supervisor, Dr. Christopher Chen, presented direct observational evidence for a specific physical phenomenon called the helicity barrier, a mechanism that had been theorized by physicists for years, but had never actually been confirmed through real direct measurement, simply because no previous instrument had ever gotten close enough to the sun to check. Understanding what the helicity barrier actually is requires unpacking a bit of the underlying plasma physics, but the core concept is genuinely graspable. In the turbulent, churning plasma near the sun, energy doesn't simply convert into heat all at once. It cascades, moving progressively from larger physical scales down to smaller and smaller ones, similar to how a large ocean wave eventually breaks apart into smaller ripples, and then smaller ripples still as it approaches shore. Physicists had long assumed this cascade continued relatively smoothly, all the way down to the tiny scales where energy could finally convert efficiently into heat. What McIntyre and Chen's team actually found, using data gathered as Parker Solar Probe flew directly through this environment, was that a specific property of the plasma's turbulence, related to a quantity physicists call magnetic helicity, essentially a measure of how twisted and knotted the plasma's magnetic field lines are, creates a genuine barrier partway through that cascade. Rather than energy flowing smoothly and continuously down to the smallest scales, it piles up, blocked at a specific intermediate scale by this helicity barrier, fundamentally altering how and where that energy actually gets converted into heat. McIntyre, describing why this specific confirmation mattered so much to the broader field, was direct about the practical payoff. This result is exciting, he explained, because by confirming the presence of the helicity barrier, researchers can now account for properties of the solar wind that were previously unexplained, including the specific, previously puzzling fact that the protons within the solar wind are typically measured as hotter than the electrons traveling alongside them. That specific detail, an actual measurable temperature difference between 2 different types of particles within the same stream of plasma, had remained a genuine unresolved puzzle for researchers, and the helicity barrier, once confirmed, offered a direct physical explanation for exactly why that temperature imbalance exists. Dr. Chen expanded on the broader significance of the finding, framing it as something considerably larger than a single narrow technical detail. This paper is important, he said, because it provides clear evidence for the presence of the helicity barrier, answering long-standing questions about coronal heating and solar wind acceleration, including the specific temperature signatures observed in the solar atmosphere and the variability seen across different solar wind streams. Chen went further, connecting this discovery to something with direct, practical consequences here on Earth. A better understanding of the fundamental physics of turbulent dissipation, he explained, along with a connection between small-scale plasma physics and the global properties of the heliosphere, the sun's broader magnetic influence extending throughout the solar system, would allow researchers to make meaningfully better predictions for space weather, the kind of solar activity capable of disrupting satellites, power grids, and communications infrastructure here on Earth. The research team also identified the specific physical conditions under which this helicity barrier tends to form and become active, adding real predictive power to the discovery rather than leaving it as a one-off observation. According to their published findings, the barrier becomes fully developed when the surrounding magnetic field strength grows large relative to the overall pressure within the plasma, and becomes increasingly prominent when there's a significant imbalance between oppositely propagating plasma waves that make up the underlying turbulence. Critically, the research team found that these specific conditions are frequently met in the solar wind close to the sun, precisely the region Parker Solar Probe has been directly exploring, meaning this effect isn't some rare, isolated curiosity. It's likely a widespread, routinely occurring feature of how the sun actually heats its own atmosphere and accelerates the solar wind outward into the rest of the solar system. What makes this discovery genuinely resonate beyond the specific technical details of solar physics is where else this same underlying mechanism might apply. The implications of confirming the helicity barrier extend well beyond our own star, because many hot, diffuse astrophysical plasmas scattered throughout. The wider universe are also, in the same fundamental sense, collisionless, meaning they share the same basic physical conditions that make this mechanism relevant. Understanding precisely how energy dissipates into heat within these kinds of environments carries broad, meaningful consequences for astrophysics generally, not just for explaining our own sun's behavior. The direct observation of the helicity barrier within the solar wind effectively gives researchers a unique, accessible natural laboratory, the only such laboratory currently reachable by any human spacecraft, for studying complex plasma physics processes that likely govern extreme environments throughout the wider universe, from the accretion disks surrounding distant black holes to the turbulent plasma found in other stars' own extended atmospheres. This wasn't the only genuinely significant discovery to emerge from Parker Solar Probe's deepening exploration of the corona around this same period, and understanding the broader context helps show just how much this specific region of space has continued surprising researchers, even as they've gotten progressively closer to studying it directly. In October 2025, a separate team of researchers announced the direct observation of torsional Alphen waves, a specific and genuinely elegant kind of magnetic wave that twists as it propagates through the corona. First theoretically predicted more than 80 years earlier, but never actually directly observed until this specific research, captured using the Daniel K. Inouye Solar Telescope, a powerful ground-based observatory working in careful coordination with Parker Solar Probe's own direct in situ measurements. And in July 2026, an entirely separate line of research, led by a researcher identified in the published study as Syed, working alongside Dr. Gary Zank, a distinguished professor of space science at the University of Alabama in Huntsville and director of the Center for Space Plasma and Aeronomic Research, introduced yet another genuinely unexpected factor into the coronal heating puzzle. Evidence that tiny, charged dust grains present even in the young near-sun solar wind might meaningfully influence how energy actually travels through the corona, introducing a variable that decades of prior research, focused almost exclusively on plasma particles and magnetic fields, had essentially never considered at all. Zank, reflecting on the significance of this additional unexpected finding, described it directly. The discovery of dust in the young solar wind by Parker Solar Probe, he said, allowed his colleague to open up an entirely new and unexpected area of study in solar physics, adding that the presence of dust could genuinely change how researchers understand this long-standing open problem, and that the preliminary results already suggested a surprising new paradigm may be emerging. Taken together, these overlapping discoveries paint an honest, genuinely fascinating picture of what it's actually meant for humanity to finally reach the sun's inner corona directly, rather than simply observing it from a comfortable distance using telescopes. The helicity barrier, confirmed through careful, direct measurement, provided the core, foundational answer to a 70-year-old mystery explaining the basic mechanism by which turbulent plasma energy actually converts into the million-degree heat that makes the corona so much hotter than the sun's own surface. But layered on top of that foundational answer, researchers kept finding additional genuinely unexpected complexity, twisting magnetic waves predicted decades earlier but never actually observed until now, and charged dust grains. Introducing an entirely new variable into a problem researchers had spent decades studying almost exclusively through the lens of plasma and magnetic fields alone. Adam Sabo, a Parker Solar Probe mission scientist at NASA's Goddard Space Flight Center, captured the genuinely open, ongoing nature of this research honestly when discussing the mission's broader findings. "We don't have a final consensus yet," he said, "but we have a whole lot of new, intriguing data." That's not a hedge or a disclaimer. It's an accurate, honest description of where cutting-edge solar physics genuinely stands right now, a field where humanity's first direct sustained look inside the sun's own atmosphere has answered one of its oldest, most persistent questions, while simultaneously opening up several entirely new ones that nobody had fully anticipated before the spacecraft actually got close enough to look. So here is where this genuinely leaves things honestly grounded entirely in peer-reviewed research published in Physical Review X and the direct, on-the-record statements of the researchers who conducted it. Parker Solar Probe, after 7 years of careful gravitational maneuvering and a sequence of increasingly close, genuinely dangerous passes through the sun's corona, gave researchers something no spacecraft had ever provided before: direct physical measurements taken from inside the sun's own superheated atmosphere. Those measurements confirmed the real existence of the helicity barrier, finally resolving a 70-year-old open question about why the corona burns hundreds of times hotter than the sun's own surface directly beneath it. And in the process of finally answering that question, the mission has continued turning up additional, genuinely unexpected physics, twisting magnetic waves and charged dust grains among them. Exactly the kind of honest scientific progress where solving one long-standing mystery reveals several new, previously unrecognized layers of complexity underneath it. If this kind of story is what you come here for, one grounded in exactly what NASA's own scientists measured, confirmed, and published, rather than exaggeration, hit subscribe and turn on notifications. Because there's clearly more genuine, unexpected physics still waiting inside our own sun's atmosphere. Drop a comment telling me which of these findings surprised you the most, the helicity barrier, the twisting magnetic waves, or the dust grains nobody expected to matter. And share this with someone who still thinks we already fully understood our own star.